also can propagate the change data output over the output. Oh, sorry, I write put is output and back to the data change over the input. So this is the main topic of this talk about bidirectional computing and the language to describe bidirectional computing, which is bidirectional languages. And using bidirectional languages, we can write bidirectional transformation. So in the rest of talk, basically bidirectional computing and bidirectional transformation will be used interleave, almost the same, have the same meaning. Okay. So I would like to talk something about short history of bidirectional transformation. So bidirectional transformation actually is not that new. It can date back to 1980s, where in database community we have called view update problem. So what view update problem is that we have a big database here. So when we want to modify this database, it's quite difficult to go through all the data there because it's really huge, it's very big. So how to deal with that? The database guys say, oh, you could do this. It's just the first, extract the information you want to modify. That means you extract a view where the data contains the data you want to modify. And then you do modification over this view. And finally, you have a mechanism to reflect back the change over the view to the change over the database. So this is called view updating problem. Means I update the big database through the update over the view. So this is 1980s. And after that, quite a lot of work actually been done in 1980s and 1990s. And we software people and we program language people would like to see whether we could extend this framework and can provide language to construct a software looks like this. So this comes up with bidirectional transformation research on this from program language perspective. So the first approach is basically called forward-based. I call it forward-based bidirectional transformation. And this is basically, I will explain the pictures later. So this is actually pioneer, the University of Pennsylvania did quite a lot of interesting work, pioneer work. So they say, oh, you could define a domain-specific language to support development of bidirectional transformation. So you write a bidirectional transformation as if you write a unidirectional get, forward transformation. And then because it's domain-specific, you can automatically derive the backward semantics from that language. So, so they define a series of languages called lenses, okay? A lens for trees to manipulate synchronization over the bidirectional transformation between data, between trees, or lens for table, a lens for string, text. So this is one method. And at the same time, actually, another group, University of Tokyo, and I belong to, actually, we worked. So what we work is rather than define a new domain-specific language, can we just bidirectionalize existing unidirectional program languages? For example, for XML, we have XQuery there, which is quite common, often used by people to describe transformation from one XML file to another. So can we bidirectionalize that so that the backward semantics will be automatically derived? But not only for XML, you could also, there are many queries on graphs. Can we do that? So we do some work on this. But all these things actually have not work on this. Say, let the user to write basically forward and automatically obtain the backward. But the problem with forward transformation is that give me one forward, there may exist many backwards. So how determine which backward you should provide? You give automatically derive one put, and this put back may not be the one you want. So how to solve this problem? So this is actually another approach. This is in 2000, I think 14, 15, after 10 years. The one backward-based bidirectional transformation is actually the group, our group developed, is that rather than ask users to write forwards, we ask the users to write put back, backwards. And because what is later I will explain, what is good things is that give me one get, there may exist many puts. But interesting things is that give me one put, there exists only one get if there exists one. So in the sense, you can write put. Actually, the bidirectional transformation is fully determined by put. So we define a language for people to write put back. So we define put back based bidirectional transformation framework and put back based bidirectional transformation language for trees, for tables, for graphs, so that you can do synchronization over them. So this is the research overview of the stories of how bidirectional transformation is developed. So, in fact, I would like to say it's still a new area and not so many people involved in that. We actually started the first international meeting at Shonan in 2008. This is perhaps the first international meetings on bidirectional transformation, where people on database community, on database, on program language, on software engineering, and automatic control we gather together. This is the one pictures in Shonan Village Center. If you have been there, you see that behind actually is Mount Fuji. Okay. So after that, we actually have a Dasu seminar in 2010 and focus on discussing about bidirectional transformation. We went to Bounce Center in 2013, and we're back to Shonan again in 2016. So I think that the community grows bigger and bigger. And there indeed summer school actually in 2006 on bidirectional transformation. I think if you are interested in that, you may find more information there because this is held in Oxford. All materials are online. And here is a list of the bidirectional transformation workshop. Okay. In addition to that informal meeting, I still have a workshop starting from 2012, and each year now we have a 9th workshop. And we are currently organized special issues on the Journal of System Software, and submission deadline will be in March, next March. So if you're interested, please consider submission to that. So this is a very short history about bidirectional transformations. So let's go back to bidirectional transformation. So what is bidirectional transformation? The topic of this talk is how to develop robust or dependable bidirectional transformation. What do we mean by this dependable? Okay, dependability. So bidirectional transformation, as just mentioned, it consists of a pair of transformation. One is forward transformation. Sometimes we call it GET. It's the map from the source to the target. Let me using the pen. Okay. Right. Yeah. Another, but as I mentioned, the target or the view from the source to the view, sometimes we call source or target, but the output, the target, is not just read only. It could be modified. After modified, there's another transformation called backward transformation or put back. It is just to reflect the change over the target to the change over the source. Okay, so actually this put back is interesting. Not just the get from the updated output to the updated input, because there's a lot of information stored in the original source may get lost because of this get. Get may not be injective. So this put back accept the original source and the updated target and produce updated source. So this is a little bit interesting. That means because we want to deal non-injectivity of get. So see one example. So this is, for example, you have a source, is a personal day calendar, where it records a list of events. Here, events have many informations, also include one information about whether it's private or not. So you would like to make all those events that are public, not private, for public use. So you could, like forward transformation, extract informations that are not private, then make it a new calendar to show to the public. Now you have a get come with this. A good thing is that now suppose this is given to secretary, and secretary say, oh, location changed from room 205 to 206. And then you could just directly modify this. And the bidirectional transformation, particularly the put-back transformation, will help you to reflect this back to there. And one interesting thing is that if you go forward again, this will exactly does not change. So this pair of transformation, get and put, actually need to satisfy certain property to make these systems real, well behaved. So this is important properties for bidirectional transformation, so called round-trip properties. So it consists of two sub-properties, get put and put get. So get put, actually here, is get put means you have a source S, you get it, you come up with a view, come up with a target, but you don't do change, and then you put back over the original source. You should not change the original source, okay? So this means no change on the target should give no change over the source. Another called put get. Actually, this is very important property. This property means I do some change over the target, and all the change should be reflected, should be embedded in the source. In a sense, you go put back this update the view target over the source, come up with the update source, and then you get again, you can recover all the information of the update target. Okay, so any updates on the target should be reflected in the source. So the second one is much more important. Now, how to develop this kind of bidirectional transformation? So what's the challenge here? So certainly one would like to say, oh, we can solve this problem. We just using any language we like. We just write a get, and then we write a put, and we develop both programs. Then we solve this bidirectional transformation problem. Yes, it is, but there's a big problem here. Particularly, it is it's very tricky to get right. As it says, you develop a get, develop a put, but you must prove that these pairs of transformations should satisfy round-trip property. So this is actually not easy, okay? And even trickier to maintain this pair of transformation. If for some reason you change one of them, you should know how to change the other parts in order to make them form a well-behaved bidirectional transformation. Means a bidirectional transformation satisfy round-trip property. So the challenge here is, can we find a way of describing this, deriving both functions, both transformations from a single description? So this is one challenge, so that we guarantee that these pair of transformations satisfy round-trip property. Now come to the main part of this talk. Is a dependable bidirectional programming. And before we discuss the details of the construction by, that means characterized by construction and verification methods, these two things, let's see, have a big pictures of what's that. So as in the short, when I explain the short histories, I have explained as one is a forward-based, sometimes also called get-based, okay? So the popular approach, you hope that you derive a pair of transformation from a single description. Well, the strict methods is that ask the user to write one of them one is write get. Okay, this is one method. You write get, you write forward transformation. I can automatically derive put. And this is actually, as I mentioned before, this is a University of Pennsylvania. It is quite a lot of work. They define the lenses, the domain-specific bidirectional languages, and show that means it's possible to design many nice DSL for people to write forward. And because it's DSL, the backward transformation can be derived automatically. And this is a defined DSL. Another way, as I also mentioned, is automatic bidirectionalization of the existing unidirectional languages, such as ATL, which is very popular for people to do transformation over models, or Query, transformation over XML, or ANCO. This is a query language, transformation of graphs. So we did quite a lot of work over this. Maybe I would like to show one simple example here. So this is actually one work we published in ICP 2007. So this is very simple functional languages. It's first order functional languages. So function f is defined over many arguments, which is a pattern and equal to some expression. The expression is just a constructor. That means some constant functions. And with a new function is defined, or the variable. So from this, you basically can define have a quite powerful first order functional languages. So bidirectionalization is that you use this language to describe a forward transformation, and the system can automatically derive put back functions. For example, here. So this is one append function. So append is give me a to list. I append it and concat the elements of the to list. Okay, so forward is just recursively defined over the first argument. If it's nil, just the second argument. Otherwise, it will do recursively. So we provide methods that can automatically parallelize that. I come up with this is the put back. Put back means give me the original source, give me update the view or update target, give you update the source. Okay, so I will not dive to the explanation of this, but this could be done automatically. So a lot of work actually have been done, as I mentioned, over this kind of get-based bidirectional programming. And because you can automatically derive put, and if you prove that the put automatically derived can be well matched with the get, means they satisfy Roundtrip Property, okay, you can be sure that your bidirectional program will be well behaved. But the problem here is that the ambiguity of put. As I just mentioned, get is usually non-injective. Non-injective means there's a lot of information get lost, go from the source to target. So when you update the target, when you go put back, usually there are many ways of this put back. And you automatically derive one. This one will not be what the users like. So how to solve that? Let me show one example. So for example, here is a simple get. Okay, this get means give me a rectangle, and you just return the height of that. So so get height is a forward transformation. Give me a rectangle which is represented by width and its height, and return its height. Okay. Now, if I change this target, change this height, for example, change the height to 2, how I should change this one? So there are many possibilities. So for one natural possibility is you change the height of this, I change the height of this. Well, this is quite natural. I keep the width fixed, don't change the width. But certainly you could also quite reasonable is I change the height and I also change the width with the same ratio. Okay, so this is actually the ratio is here, it also reflects the width. This is, you can prove actually this backward transformation, it also can form a well-behaved bidirectional transformation with this get. In fact, there are many such kind of puts. You do some change over the output, over the height, you basically can change this width as any number you like. So you can have many. So which is the best? It is actually quite difficult to decide. And actually, in database community, it says there does not exist an order to say which is the best one. Okay. So we need a way to describe which the intentions are put back. So when we do get-based, we really need to think about that. And some people actually think how to enrich get with more information so that could control the putback. So this is quite a lot of work done there. So since the first work by Forsters in University of Pennsylvania, and that is simple lenses. And then in order to have more information over the control, over the put, they define quotient lens, they define matching lenses, and many this kind of lenses. Enrich the get with some additional information so that you can have some ways to control the putback behavior. But the thing is that you can define too many versions of get. When you need this, of course, you say, well, domain specific. When you need something, you enrich that, and then you come up with a new one. But this is really a bit ad hoc. So could we have more general methods? So this exactly what the putback based bidirectional transformations come to play. So this is, as I mentioned just during the history explanations, there's an important but little known fact is that for bidirectional transformation, you have a get forward. There exist many put that can paired with get to form a well-behaved bidirectional transformation. But give me a put, if it is well-defined, if there exists a get that can paired with this put to form a well-behaved bidirectional transformation, then such get is unique. So in other words, put uniquely determines get. So in theory, get is not necessary because if you define a put, the get is automatically, not automatically derived, is determined by put. So what is essential bidirectional transformation is nothing but write a correct put so that we can guarantee the get exists and they can form a well-behaved bidirectional transformation. So this is the techniques currently what we are developing. And I think this is more important. But there's still one problem with this putback. One is that we can easily write a wrong put. So this is one we have seen just now. This is the correct one. You have get, okay, just to return the height. And when we go some change, I just reflect the height change over the original rectangle, just to change the height. But if you define this way, so this is a wrong way actually. I put back, I have the original source is with a width and edge here, and the update height is h prime. I usually use this this update, and then say I return a new rectangle with a width of 1 with a height of h prime. And it looks quite okay because I change the height. Correct height will be the same, but the width, I change the width to a constant 1. Looks good, but actually this is wrong. You can see if initially the height, the width is 2 and the height does not change. If you use this putback, you will change the width from 2 to 1. Even you don't change anything over the view, you will change the source. So this means the get put property will not be satisfied. In other words, for this put, you cannot derive a get that can be paired with this put to form a well-behaved bidirectional transformation. So how to avoid this? How to develop a dependable bidirectional transformation? Still big issues here. So we are thinking about how to develop a dependable framework to develop well-behaved put, so that guarantee there always exists a get, so that we can derive a pair of transformations that are well-behaved. Now, how to develop dependable bidirectional transformation? As I mentioned, there are basically two approaches. One is characterized by construction. So we define a DSL. So if you're using our DSL, we can guarantee this DSL for people to write put, not write get. So this is completely different from the traditional approach. And we can guarantee that the get will always exist get, and such get can be paired with this put to form a well-behaved bidirectional transformation. So another approach is let users to write put in a familiar language they like. And then we want to verify that put is well-behaved. Okay. So the first one is we call Beagle, and I'll explain later. And the second one is birds. So Beagle like dog name, and birds like birds. It's birds, right? Okay, so let's see what is a Beagle looks like. Beagle is DSL for write put back transformations. So this is it is, I would like to say, the first put back based bidirectional languages. And as I explained before, it has full control of bidirectional behavior, because bidirectional behavior is determined by get and put, but get is determined by put. So if you can write put clearly, then you can write all the behavior of the put, of the bidirectional transformation. So in that sense, it's full control of bidirectional behavior. And it can guarantee a well-behavedness because you have a put, and we can derive get semantics. And we use ACTA to prove that this semantics always guarantee the round-trip property. And another good thing, not only theoretically interesting, it's also very fast. And in a paper in 2007, which is a bidirectional transformation workshop, some comparison of the existing engine, this actually is the fastest. And we provide axiomatic basis for reasoning about bidirectional transformation. Because when you, for sequential unidirectional program, you have a specification, and you want to automatically or systematically develop correct sequential program, unidirectional program. Here we also provide a method, which is very much looks like a Tony Hall logic style for people to reasoning about bidirectional program. So I will explain it briefly. So Beagle is actually very, very simple. It is implemented in a Haskell library. Okay, so I think you can install that. And as I just mentioned, the summer school, actually we have all the materials about Beagle there. So the language is so simple is that, as I wrote here, it is only consists of two primitives. Two primitives is replace and skip for write put behavior. It's so simple. And then you have three combinators. That means combine smaller put back transformation to form a bigger one. One is a sort of rearrange source, and then do before doing bidirectional transformation put back, and product of two bidirectional transformation and case analysis, like if condition parts. Okay. So just to briefly explain that. So replace just say, oh, what I put? I have the source, I have the view. How I do put means I replace the source. I ignore all the information of the source, just to replace that with the view. So this is a replace. For this replace, there exists a unique get. And you can see this get is only this get. The get is just identity. So for example, this replace is forward transforming, give me 1, it will give you 1. And for put back, is replace the source with the view. So if this is done, it will return 5. Yes. So this is 1. So this, the semantics of this is this one. Okay, this is the put back. And this one, this get, is automatically derived and unique. So another primitive, only have 2 primitive. One is just a replacement. Another is a skip. Don't allow any change on the view. Okay. And suppose the forward transformation A to FA, apply the function to FA. And it does not allow any change over this output. So if you change, then you say, oh, this is error. So for example, you do get, you're using double function to do get, then you double it, become 2. And then if you, this is 2, 1, because you don't do change 2, it's okay. But if you change something, you will error. So this is you provide a way how to fully embed the view to the source or complete don't allow any change of the source. These are important primitives, only these 2. And then we can combine smaller one to form a bigger one. So combinator is, the first one is called rearrange. So when you do bidirectional transformation, you may do some natural transformation over the source or over the view so that you can align the source and the view so that you can do bidirectional transformation. This is a rearrange S. So for example, suppose you get, this get is 1, 2, 1, 2. Okay, and this is rearrange means I first rearrange the pair to be just the Y, just output Y. And then I do replace. So this one is actually for get, it's just the return Y, Y2. And when you do put back, how to put back this 5 is first XY return to Y, 1, 2 return to 2. Then 2 will be replaced by, using this replace by 5. And then this 5 through natural transformation go to 1, 5. So this is one thing. So there are another 2 important composition. One is natural sequential composition, parallel composition, and case composition. So I will not explain them in detail. Just return to the examples we just mentioned. For the height, for example, for this kind of height, we just change the height. When we go back, change the height of this source of the height with the view height. So we just we rearrange the source first and return its height, and then this will be synchronized using replace with the output. That's it. Certainly, you should say I can rearrange the view first, extend it with a trivial width, and then I use width to update on this and view update on this. This is another way. So this is the rearrange view. View becomes a pair. This don't care width, okay? And then for the view, this corresponds to the height. I use it replace. And for the first part, I just say don't change. Okay, so this is, so user writing this program, okay, guarantee that it's always well behaved. So this is one method, characterized by construction. Of course, when you, this is just satisfy round-trip property, but sometimes you say, I want to develop a bidirectional transformation and such that it satisfies other conditions, okay, other properties. You can do that. And for example, then you can construct a logic, such kind of looks like whole style logic for you to reason about that. I show a little bit idea about that. For example, here is a replace. So replace, you can see initially, you can see we can construct a whole style logic for that. So replace, you know, it is just give me a source, give me a view, and return a new source, which is exactly the view. This is I explained just now. Now you can write this property as what is a precondition for replace. what is the post condition for that? So post condition is that we actually, for the output, we have the update source, original source, and view, this triple. This triple has property where this S prime should be the same as view, as update view. This is a post condition after this replacement has done. And what's the precondition? The precondition is that for the original source and view, I don't care. It could be anything, so it's true. So you build up this kind of rules, okay, precondition, postcondition, and you can construct all of them for other constructors. Others failed, skip and case product, and then you could do reasoning. So I look at the time, maybe not so much time for that. I will skip that. For example, you could do, say, this is exactly the example I showed before. So this is the bidirectional transformations for put back of the height to rectangle. So for input, I don't have, for the original source and view, I don't have any requirements. But after the put back, this is the updated source, is a new rectangle. This old rectangle, this is the view. I need to prove after this has been done, the height of the updated rectangle should be the same as view. And the width should be kept the same through this program. And then this is a style of whole logic proving. So I should show that. I will not explain in detail. You can do that now. Okay, so much for the first methods characterized by construction. It's birds, not birds, it's beagle. And second is that we could allow users to use the existing approach, existing languages to describe put. So, this is bidirectional transformation originated from database community. So the first target is a database people. Okay, so we do that. So we build a birds framework for doing that. So this is a verification approach. This is a big picture of that. So we allow users to use Datalog to write put, okay? And then we do validation. This validation will guarantee soundness and completeness. So we'll later explain. And when we do efficient implementation and we show almost existing view updating problems can be solved. So I will basically focus on these two. Actually, for the first one, you see how to represent the updates in Datalog program. That is one thing we need to think about. So the idea is that, I think, sorry, it seems there's some echo. How to turn off? Oh, so it's fine now. Yeah, it's fine now. So for tables, actually, for example, for a table tracks, this is a tracks information. And if we want to represent the updates over the tracks, we can use two tables to do that. One is a deletion table, say which tracks records the tracks which will be deleted, and insertion table, which have the tuples that need to be inserted. Certainly, this deleted one should originally exist in this original table. And this deletion table and insertion table should be disjoint, okay? So if that, then we can represent updates of the tracks. Now, how to write put? Put is give me a source, give me a view. I want to give an updated source. Now, how to do that? So we design. So give me a source, give me a view. You could write put in two steps. First, you just you give me a source, give me a view. I produce update tables over the source. If you get this later, it's easy. You just apply this updates over this source. You come up with update source. So the central part is this part. Is go from the source and update the view, come with the update tables over the source. So important things is the put is divided into two parts. One is put data, Another is a trivial applied updates over the table. So important thing is this one. Let's see one example. So suppose this put. This is source, suppose is have two tables, which is S1, S2. And the output is a view. Is a view basically intentionally is this view is a union of S1, S2. But of course, this is allowed to be changed. So initially it should be 1, 2, 3. But if we change 3 to be 4, then how I can reflect this change to the source so that the updated source, the union of updated source become this view. This is a putback. So we can do that. So this is actually the program user need to write this strategy put in order to synchronize these two. The only thing they need to write is just this. He said, what need to be deleted from S1? What need to be added to S1? This is defined. What need to be deleted from S1 is initially it was in S1, but now it is, but it's not in view in the view table. Then it should be deleted. Similarly for S2, but what need to be added to S1 and S2 because it's union. Suppose we do bias. There are many strategies. We just if something new things added here, we just put it to S1. So this is a strategy. I add to S1. What need to be added to S1 is it is existing view, but does not exist in S1 table and S2 table. Okay. Certainly you could say, oh, I could also add to S2 because the union is fine. Or I don't add to S1, I just add to S2. This is all okay. And this is actually shown for one get, there are many kinds of put, and all these intentions should be described. So for this example, we get this result. But then is this put data correct? Means can you come up with a get? Then that compare with this put to form a bidirectional transformation. Actually, this is correct. But if you don't forget to write this one, it actually becomes incorrect. So how we can validate these things and how we can find this error is one thing interesting. So we do validation. So validation algorithm is basically give me the Datalog programs and when we do automatic validation. Certainly Datalog is very powerful and you cannot deal with any Datalog to do this kind of validation. You should choose a subset that is powerful enough, useful enough, so that you can do. So actually the class we defined is called LVGN-Datalog. What is a GN is quite well known in the Datalog community. It's called guarded negation. That means when you define this clause, okay, this is actually say if this satisfied, imply this one. So what is a guarded negation? If you have negation here, all the variables in the negated part should be bounded somewhere. So should be bounded by positive things. So for example, this x1, x2, x3 is negated, but x1, x3 should be guarded, should be bounded by a positive things here. Okay, this guarded negation. This is a well-known concept in Datalog community. Another is a linear view. So this is quite problem specific. So for us. So because we need to later derive get functions. So what a linear view is that the view table appeared in the right-hand side only appear once. So for example, even it's in the negated form, it's fine. This appeared once. But this is not appear once because this is a don't care things. So if you instantiate this part, you can have many such kind of V. And this appear twice is self-joined, it's not allowed. Okay. So the validation algorithm basically consists of go from this LVGN-Datalog to validation. It is just first check the overlap between insertion and deletion tables. So the insertion table and deletion table you build should be disjoint. Otherwise, we'll not be able to say more about later things. Then we check get put property. The last thing is that you give me a program which is in an LVGN form, we can encode the get put as the Datalog programs there too, still in LVGN form. And this LVGN form can be mapped to SMT solver to solve that. And then through that, we can guarantee the existence of get, and even we can derive this get. And then we check put get. Actually, put get can also be encoded using LVGN-Datalog. And then if yes, it's valid. Otherwise, it is just to say, oh, it's wrong. So all these things is decidable, has been implemented using SMT solver. So this is a theoretical results. So it is sound means if any LVGN-Datalog put back programs pass all the checks in algorithm 1, it is indeed valid. Invalid means it's well formed. Okay, exists get compared with it from a well-behaved bidirectional transformation, and it is complete means any valid LVGN-Datalog putback program actually will pass all the checks in algorithm 1. So for details, you can take a look at this year's VLDB paper. So for efficiency, we actually do quite a lot of things for efficiency. We test almost all the examples in the view updating problems in database community. Okay, and for detail, I will not explain that things. If you're interested, you are welcome to try these bird systems, and with all many examples demonstration there. Okay. So I think almost times I do quickly show some applications. Actually, this is bidirectional transformation is quite interesting. We started this work about 10, 15 years ago. And so at that time, we developed one system, University of Tokyo. Actually, our department, actually at that time, tried to use these systems. So it's modifiable websites. You know, when we build websites, there are many information actually need to be consistent with each other. And how to do that? And people usually change the database behind. But here we provide a way that anyone can modify the web page just through the over the web page. What you see, for example, this shows our lab website at that time called Programmable Structured Document PSD in University of Tokyo. And then, for example, for publication, you have to click that, you can change that. And then you go back and all the information, all other websites related to this will be automatically changed. So this is actually bidirectional transformations plays a role behind. So each website considered as a view of the database behind. When you do some change over one view, you just go back to the source and regenerate all the other website page. And so all the information will be keep consistent. And you can apply this to do code and model code evolution. For example, we have tried to see Java code and UML class diagram. They could be done through bidirectional transformation. You could keep maintaining invariant traceability. Okay, keep them code evolution. And if you want to do program write compiler or some things, you usually take a lot of times in synchronize between source program and abstract syntax tree. Because you do find some bugs or you do some change optimization over this. You hope this should show to the users where the original program is. So you need a synchronization between these two. So we develop a by yuck. And like a yuck, okay, so you write that put back rule rather than production rule. And then you can get that. You can do change over the syntax tree into optimization and things, you can go back automatically. And recently, we also do some things, modern-driven design of city spaces. You have a city GML, which is describe the city space, okay? And then you want to check whether this actually is a correct design. For example, when some accident happens, people can evacuate them quickly, such kind of things. Then what you do is that you extract a sort of analyzable models here. This is currently we use bigraph. Okay, analyze models here, and then you do analysis or change here, and you could go back. Okay, so this is one thing, one applications. Finally, I would like to maybe I still another interesting application is that now currently we have many agents, okay, on the cloud. We want to share data, but privacy is very important. You have privacy problems. As you see, bidirectional transformation can control what data should be shown to others, what data can be modified on the view, and what cannot be. So you give your privacy policy and the data you want to share with others, I can automatically produce a bidirectional transformation to control privacy so that you can share data in a safe way. And finally, this is recently published in ASE as a distinguished paper award paper. So it is you want to so you usually have models here. For one model you need to satisfy many properties, and then you say, oh, many properties, 1, 2, 3, and you actually could slice these models to different views so that according to each property automatically. And then you do this kind of analysis or modifications for each view. And then you can combine the results. So here you see bidirectional transformation happens here. So this is, I think, come to the summary, almost time, the summary. So I think bidirectional programming is a new program paradigm. It's quite important, particularly for data synchronization. And when we do this programming, nothing but develop, put back. And we show two methods for a dependent bidirectional programming. One is Beagle. It's a bidirectional, it's a domain-specific language for people to write only well-behaved put-back bidirectional transformation. Another way is verification methods allow users to use Datalog, a small class, a subset of Datalog, to write their put, and will provide some complete validation methods for that. Okay, that's it. Thank you very much. Sorry, it'll be too long. Yeah, thank you.
Yeah, thank you for Professor Hu's wonderful talk. Now we're open for questions, so anyone just can unmute your speaker and ask your question, please. Okay, maybe let me start the first question to motivate others to ask. I think it's the techniques, the bidirectional transformation is very useful, quite general. One of the recent research trend is talk about explainable AI and verified AI. So there are many transformational approach which transform like deep neural network models to decision trees, and the transformation to probabilistic models or like MDP models. There are papers in recent conferences and the journals.
Right.
So it's perhaps Professor Hu can share some light in how bidirectional transformation programming techniques may be able to apply to create a dependable intelligence for correct, reliable transformation approach for explainable AI and verified AI.
Yeah. This is really interesting, really good questions. Yeah, I've thought a little about that. I'm still studying about that because this is a little bit complicated. I actually, frankly speaking, I don't have a good idea yet, but I think it has it's a really nice potential applications for that. I would like to see more about that. Yeah, so for now, I don't know. We don't have result about that. Yes. So it's a really good directions for the research. Yeah. Because when I studied,
particularly I think that one of the easy ones may be looking at people doing kind of a repairing when some decision was wrong. Maybe some of the data was kind of corrupted or attacked the data, somehow they can remove this kind of data that's kind of updates the certain data, then maybe transform it back and then make the decision more correct. Maybe that was kind of a starting point to look into how bidirectional transformation technique applied to deep neural network repairing that kind of work. Maybe I'm just
yes.
Very new. I mean, only very recent.
It's really interesting. Yeah, we would like to investigate.
And then we can chat. I have a post of Lin Yun's looking into that, and Xiao Yan. I mean, maybe we can chat about it later.
Okay. Yeah, great. Yeah, thanks a lot.
Yes, everyone else, please ask questions. I think it's very generic, wonderful techniques, can be applied to many application domains.
So I see one guy.
There's actually a message. Maybe I should read about it. So the message was like, I may have maybe
Can you directly ask the question?
Ask directly.
Yeah, hi. Thanks for the talk. It's great to see. It's great to see some formal things happening into programming in practical ways. It's good to see that. I was curious about the definition you're using for the equality when you define the replace.
Okay.
So yeah, you have the full question here, but just to summarize the.
Right. I can show you. You want to see that slide?
You can show the slide.
Okay.
Yes.
Yeah. I can share that.
Just to make sure that I fully understand how you define the views, because typically in object-oriented programming or in database, view is just a partial part of the bigger picture. So sometimes you may replace by something that is not completely semantically equivalent. So I was just wondering if in your case, views are always semantically equivalent and you replace one view by something that is semantically equivalent.
Right. So replace. So actually there are some tricky. So let me see this one. Okay. So it's not just equivalent. So these are four things. So replace can only do equivalent things because they're basically the same thing, does not lose information. Skip, don't allow any change, but this is not so interesting. But actually there is one hidden here called rearrange S here. So this rearrange, what do they do is that they can project some information. They can do some called natural transformation. They can, but only, that means does not relate to the, you can extract some part of the information from the source to the out of it, and then restructure it, and then align with the view to do things. And this kind of natural transformation, polymorphic, you can basically use a sort of, theorem for free. You could actually do this kind of bidirectional transformation easily. So this is done by rearrange. So this actually the only way you get information lost. But information you get lost must be sort of natural transformation, structure transformation. For structure transformation, you can guarantee the bidirectional transformation. Even if it is not injective, yes. So this is tricky. Yeah.
Okay. Thank you. Makes sense.
Welcome. You're welcome.
Okay, perhaps we have time for one more question.
Hi, Prof. This is Lin Yun from NUS. Thanks, Prof, for the great talk, and it is really inspiring and thought-provoking. My question is that sometimes the target model is an aggregation of the information from the source model. That means it makes the forward transformation possible, but the backward transformation a little bit ambiguous. So that, in other words, the backward transformation becomes somehow probabilistic. So is that possible to using some machine learning? Have you ever think about it to using some machine learning based approach to learn the probabilistic distributions, or even using some user interaction based approach for this issue?
Yeah, it's really good questions. It really, we are trying to see how to do that. Yeah, so actually for putback, you write put back, you don't want to fixed, very fixed how to do the behavior. Sometimes you need to use proper non-deterministically. That means use proper deterministic methods, or even you would like to interact with the users so that you can have a good backwards transformation. But all these things currently you see, all our languages basically is a sort of pure functional or pure logic. So it's quite interesting to empower the bidirectional transformation languages with effects. Like actually the probabilistic, this kind of behavior can be captured by effects, or people say monads, and or others. And this is really interesting. We are thinking about that because you need to reformulate the round-trip properties about that.
Okay, thank you.
Yeah, it's really interesting. Yeah, very good questions. Yeah, we are thinking about that. Yes.
All right. Okay. Thank you so much. Thank you, Professor Hu, and everyone participate in this conference. And yeah, we're going to chat a little bit more with Professor Hu and in this area. Next, I'd like to introduce, I think there's a continual technical session straight away in this online meeting. For the first technical session will be chaired by Shangwei Guo. So perhaps the co-host can pass to Shangwei Guo, and we'll continue the technical session without a break, actually.
Right.
There's another session. Yeah, there's another session will be moved to a different, please look at the guideline to click the link, the Zoom link to go to other session. There are 2 parallel sessions right now. Yeah. Thank you so much.
Okay, thank you very much.